Now we'll move on to the equivalent circuit model of diode. So Shockley's equation, right? Shockley's equations give the exponential relationship between current and voltage. But every time while using diodes in a circuit, we do not need to apply the exponential formula to find the values of voltage or current because it's too accurate. We don't want accurate stuff in physics or applied physics or anything basically. Who needs accurate stuff, right? So we can approximate the characteristics of the diode by replacing the diode in the circuit with its equivalent circuit. So an equivalent circuit is nothing but a combination of elements that best represents the actual characteristics of the device. In simple language, it simply means the diode in the circuit can be replaced by other elements without severely affecting the behavior of circuit. Diode can be modeled in 3 different ways depending on the accuracy required. And these models are just where we convert a diode into something else. A bit analogous would be where we converted batteries diagrams with internal resistance to a battery symbol and a resistor symbol, if you remember in 12th class. Yeah, it's probably a bad analogy, but I guess you guys are smart enough to get the point here. So the models are ideal diode model, simplified diode model, and piecewise linear model. So first we'll go on with ideal diode model. Ideal diode model. I'll draw its IV graph here. Very bad line, but it is what it is. What you can do about it. Oh, that was good. And let's do the current width. Yeah. So ID and VD. So ideal diode model is nothing but a switch, right? The ideal diode is equivalent to a switch as shown in this figure. You can see here, it allows the forward current for any value to flow for forward bias voltage while not allowing any current to flow in reverse biased. As you can see from here, there is no reverse saturation current or breakdown voltage or anything like that. So we can write these 2 points above the ideal diode basically. First is it allows the flow of forward current for any forward bias voltage without any impedance, right? It acts as a closed switch. A closed switch. And an ideal diode under reverse bias does not allow any current. So it basically acts as a open switch, right? Easy enough. So the model would be, so in a circuit, you'll basically are diodes. So let's say if this is the diode, this is for reverse biased. So in reverse bias, you can remember N2 plus. So this is the N side, this is the P side, right? So in the reverse biased, we'll just show it as an open switch in the circuit. And you can also do it like this. And in forward bias, it will become plus, it will become minus, it'll act like a closed switch, minus plus or. So this will be converted into this, basically. So if we have to like show a diode in a circuit, we have this circuit, right? So we can just basically either show it with an open switch or a closed switch. Now we'll move on to the simplified diode. So if I draw the simplified diodes graph, thank you for the beautiful lines. This time we'll use red. So ready, VD. The equivalent model in this case, like for simplified model, consists of a battery and an ideal diode. So like consider this horizontal line, right? So let's say we have a battery of 0.7 volts. Okay, 0.7 volts. So we take batteries according to what diode we are representing, right? If their knee voltage is like 0.8, 0.7, something like that, then we'll take diodes like that. If not, we'll take different diodes, right? But it's not like diodes themselves are, you know, source of voltage. We're just like modeling them. So in a circuit model, a diode would basically become, again, this is just a model, right? Nothing else. We have put a battery here. And this is an ideal diode, okay? Right? Easy enough. So in a simplified diode, the diode model would be, I'll highlight it, this part. So this is the diode, okay? Plus, minus. So why are there diverse polarities here? So the battery here will oppose the current until the voltage is 0.7 volt, right? That's why we've placed a battery here. So in this graph, the battery from here to here, it will oppose all the current, and only when the voltage is above 0.7, it will allow any current, right? And thus we have an ideal diode. This is the model for an ideal diode. Now we'll go to the piecewise linear model. Piecewise linear model. So the piecewise linear model, as the name suggests, is a model which the characteristics of diode is approximated by piecewise linear line segments. So if I make a IV graph like that, so our real diode would actually, sorry for the bad line, so our actual diode will go something like that, and our piecewise model will represent it somehow like this, right? So let's say this is 0.7 volts, and this will be 0.8 volt. This will be 15 milliampere. This is current. This is V. So this is basically where there's, you know, some sort of resistance, right? Consider this graph. Consider this line. Consider the, you know, straight line in this piece wise linear characteristics. This is a straight line. I've not drawn it correctly. It should be something like that. But yeah, consider this. So this straight line indicates constant slope, and slope in a VI graph basically means a resistance. So what do we do? So this is basically this graph, but with an added resistance to it. So now what would we do for the model? So for the model, we have, this is a diode, right? This diode changes to, this is our positive terminal, this is our battery. So first we'll make that, we'll put an ideal diode. And then we'll just put a resistor there. So this whole thing is now the piecewise linear equivalent model of a practical diode, right? So this is most accurate You can see it's not the same, but for these curves, you know, at like voltages like these, it's not like same at the knee, but it is a good it is a good first approximation. For simplified model, for ideal model, this is just basically a open switch. But again, according to our needs, we can choose one of these models, right? So now let's just think, what's the resistance, this resistor value for this diode, right? So this, it is nothing but like in VI graph, you know what a average resistor value is, you know, V over I. V is, it would be 0.8 minus 0.7 over 15 milliampere, because it goes from 0 to 15 milliampere in the region of 0.7, 0.8, right? This will come out to be basically, this will come out to be basically 6.67. Not 6.67 ohm, right? So we learned about ideal diode, simplified diode model, and then piecewise linear diode model. Now we learn about breakdown phenomenon in diodes. Okay, let me make a PN junction. I'm sorry for that bad line again, but what you can do, P N plus minus. So this is reverse, but our breakdown happens in, this is forward, our breakdown happens in reverse voltage. N is for positive, P is negative. So this would be reverse bias. So we know that the breakdown voltage is the largest reverse voltage that can be applied without causing an exponential increase in the current in the diode, right? Now, note that as long as the current is limited, exceeding the breakdown voltage of a diode will not destroy it. I talked about, you know, exceeding the breakdown voltage and an avalanche happening and our diode will be broken down. That's not true. If the current is limited, the diode still can function under breakdown voltages, but yeah, like we don't want the voltage to be, you know, like very much. We need to control the current. So this is very similar to breakdown in insulators, as you may know. Like if we have voltages high enough, we can ionize the air and then we have these arcs. So the breakdown voltage there is the voltage at which the material conducts uncontrollably. There are two breakdown mechanisms that exist in diodes, which are basically Zener breakdown and avalanche breakdown. So in Zener breakdown, the electric field established due to the reverse voltage is high enough to get the electrons out of their covalent bonds and away from their parent atom. So if you remember, in this energy band diagram, right, this is valence band, this is conduction band. So Zener breakdown is when like our voltages are high, but they're like not extremely high. They're high enough that these electrons in the valence band go out into the conduction band. So the increase, so from P, they start going towards N. And current starts flowing down, right? These electrons are then essentially have moved from the valence band to the conduction band. And like in this situation, we can limit the number of free electrons produced by the applied voltage. So, you know, it is possible to cause Zener breakdown without damaging the semiconductor. And this is like used in devices and which is also known as Zener diodes. You'll like we learn about that in the next video, Zener diodes. And like Zener diodes are diodes which operate under Zener breakdown voltage basically. Now, the other type is avalanche breakdown. So in avalanche breakdown, the voltages are so high that these valence band electrons are so, like they have so much speed that they collide with other atoms and electrons. They knock those electrons out as well, and then those electrons knock other electrons out. Due to the electric field, they accelerate so much, they get so much kinetic energy, like all the electrons start going to the conduction band, and a big flow of current happens, and our diode is carbonized, and then it's dead basically. So that's like, it's so exciting, destroying something. Yeah, let's imagine I did not say that. But yeah, there's an exponential increase in current and our material is destructed. So one electron, it basically goes like, nuclear blast. One electron knocks out another one. Now these two electrons, this will knock out another one, this will knock out another one. Now these 4 electrons will knock out 4 other electrons. Now those 8 electrons will not knock out another 8 electrons. And then there will basically be an exponential increase in the number of electrons knocked out. That was a very bad line. That's not an exponential increase, but yeah, an exponential increase is there. So this is very much analogous to our nuclear explosions. So think about Zener breakdowns as nuclear reactors, right? Zener breakdown as basically nuclear reactors. So in Zener breakdown, we are controlling the amount of electrons that are being knocked out, right? And hence we can control that it does not, just go boom. But in an avalanche breakdown, it's basically a nuclear explosion. This was a very good analogy. I do not know why I didn't think of that earlier on. But yeah, that's it for today's video. And yeah, I hope you liked it. And please, subscribe, like, at least comment. Tell me how it was, how I can improve stuff. Tomorrow we'll learn about, Zener diodes, diode characteristics, diode as a capacitor. I'll be crunching out videos every day. They take a little bit of time, but yeah, I'll be doing that. And I hope you liked it, and good day.